Hello, everyone, and welcome to the last section of continuous function. We're going to talk about one of my favorite theorem of the whole semester, the intermediate value theorem. This theorem is so crucial because it's so beautiful. No, because one of the tool that I'm completely in love with that we've been using for a while already is sine tables. And the reason why sine tables works the way they work, it's because of the fact that we're doing it on continuous function. And remember, when you're constructing a sine table, the first thing you do is you find values where the function is not defined. You find also values where the function is equal to 0. And then in between, just by doing one evaluation, you pick one point and you compute the output. And if it's a positive output, then you put a plus there. If it's a negative output, you put a minus there. And that process only works because you're dealing with continuous functions. And we'll talk about that in that section. So it's really a piece of theory that comes to really support this very important tool. Anyways, okay, I'm always like this. I talk too much, okay, because I'm alone in my basement. It's so cold. Anyways, so what is the intermediate value theorem? I might refer it as the IVT times 2 times. So if you have a continuous function on a closed interval AB, and suppose we have a number, let's say big N, that is any number in between f of A and f of B, assuming, of course, here that f of A and f of B are not equal. If not, there's not a lot of room for any number in between. Then for sure, there exists a number C within that interval that will be such that when you evaluate f at C, you get that number back. You cannot skip over any number because, of course, if your function is continuous, you need to draw it, from that lower value to that upper value without skipping on any of those values. So the intermediate value theorem should be absolutely be intuitive. And here's like an example visually of what I mean by this. So here in magenta, I drew a function f of x over an interval AB. And if you pick a number, let's say we start with n here, in between f of A and f of B, then we see that there's a corresponding x between A and B that is such that, so that I labeled C here, such that f of C is equal to n. You can have one, you could have more, of course, like as an example, I've also did the intermediate value theorem for another number that I call big M. Here for big M, there's 3 x's, C1, C2, and C3, that are such that if you compute f at C1 or f at C2 or f at C3, you're going to get M again. Okay, so the intermediate value theorem does not tell you how, to find these x's, but that theorem assures you that there's some x's out there that will do the job. Man, that sounds so depressing. Anyways, just a small remark about the intermediate value theorem. You have to be careful if you're outside. Like if you think about, is there any x's that gives you values, like for example here visually bigger than f of B or smaller than f of A? You just don't know. And here you can see that the function actually goes lower than f of A. So the only thing the intermediate value theorem tells you is about the intermediate values, and it knows nothing about what's going on above or below the maximum number or the lower number. So it could go above or go below. We just don't know. Okay, but for sure, we are covering everything in between f of A and f of B, okay, for continuous function. So how can we use this intermediate value theorem? So the next example is a classical type question where the intermediate value theorem can be used to find roots for function, or at least find intervals where the function has roots. So for example, let's show that the function x to the 5 minus 5x minus 2 has 1 positive roots and 2 negative roots, at least 1 positive and at least 2 negative. Of course, functions of degree 5 could have more, but we will not find them, okay? We will not find all of them. Actually, we will find all 3 of them. I mean, we will find 3 intervals for all 3 of them, but in general, you could have all the way up to 5 roots. Anyways, so how do you find roots with the intermediate value theorem? So here's a big trick. This is very, very important. So a trick to find roots for continuous function, just construct a table of outputs. And then as you construct a table of outputs, if you find any sign changes, so if you compute an output and you get something negative, and then you move a little bit further and you find something positive, then by the intermediate value theorem, if your function starts somewhere negative and then it needs to go up to somewhere positive or vice versa, then of course by the intermediate value theorem, assuming that the function is continuous here, of course, then you will need to cross the x-axis. You will need to have like a root somewhere. So that's a very, very, very powerful statement. So if you compute a bunch of outputs, anytime you change sign, you have a root in between. So for sure. So very, very cool thing to notice. So here, if we want to find a positive root, so let's start at 0. So here I made a little table. Let's compute the output at 0. So at 0, if you compute the output at 0, you will get 0 to the power 5 minus 5 times 0 minus 2 and get minus 2 out. So be careful here. Forgot to label my stuff, but my first column is for x. My second column is for f of x. So at 0, we get minus 2. At 1, if you compute the output at 1, so 1 to the power 5 minus 5 times 1 minus 2, you can double check. This gives you minus 6. So right now, between minus 2 and minus 6, we're not changing sign. Maybe there's a root, okay, but we just don't know. But then if you compute the output at 2 to the power 5 minus 5 times 2 minus 2, you get 20. You go from negative to positive. So because you go from negative to positive, you're changing sign. So here we go, poof. Okay, so we have a change of sign. So we go from positive to negative, so negative to positive, sorry. So there is a root in between 1 and 2 by the intermediate value theorem. Where is it? We don't know, but we know there's 1 in between. So we found our one interval where there's a root. According to the question, we need to check that there's 2 others negative. So we'll go backward now. So if you compute the output at minus 1, you can double check that minus 1 to the power 5 minus 5 times minus 1 minus 2 is going to give you plus 2. Whoa, change of sign here. That is perfect. So here, between minus 1 and 0, it goes from positive to negative. So here we go, boom. Okay, we have a change of sign. So it goes from positive to negative. There is a root, okay, between minus 1 and 0 by the intermediate value theorem. And then if we compute the output at minus 2, you can double check that minus 2 to the power 5 minus 5 times minus 2 minus 2 is going to give you minus 24. Another sign change here. So it goes from negative to positive. So we know that there is another root here by the intermediate value theorem. So here we go, boom. Okay, so there is another root, okay, between minus 2 and minus 1 by the intermediate value theorem. So something I forgot to mention, of course, if we have a polynomial function, okay, so this is very crucial. You have to mention this first always when you're doing that trick, poof, that the function f of x is actually continuous everywhere in this case. So you can only use that trick. You can only summon the intermediate value theorem if your function is continuous. Okay, so over the intervals of studies. If not, this is not going to work out. Okay. All right, so again, you're looking for roots, just compute outputs. Every time you change sign, you naturally create an interval where the root lives. And now the last delicious theorem that makes a link between the intermediate value theorem and sign tables. Sign tables, one of my favorite tool in calculus to study functions. So a beautiful tool. Okay, so if you're not in love with sign tables at this point, I don't know what I can do, okay, for you. It's precious. Anyways, so what is the link here? So I'm just going to read over. I mean, you don't have to worry too much about this theorem. What really should concern you is that you have to know how to use sign tables. And of course, there's theory behind it that you need or not need to know. But the reason why these sign tables work the way they work, it's because the functions we're studying are initially continuous over their domain. Anyways, so let me read the statement. Let f of x be a function that is continuous over a open interval ab if f of x has no root inside ab. So if f of x is never equal to 0, then either f of x is always positive, strictly positive, or always strictly negative. Okay, so in other words, if you pick any point in between AB and you compute the output at that point, then the sign of the output is the sign of the whole interval. And we've been using this a lot already. Okay, so if this is like breaking news right now, I don't know what to say. Okay, so we've been doing this so much so far. So again, here I'm going over the proof. I think the ideas should be very intuitive, but the way the proof works, or one way to make this proof, to present this proof, is actually by assuming the opposite and proving it by contradiction. So here the proof will be done by contradiction. So what do I mean by this? It's suppose the function has a point somewhere where the function is negative. So suppose there's a point, let's say n for negative. Suppose there's a point between a and b such that the output is negative. So f of n is strictly less than 0. And suppose there's another point, let's call it p for positive, in that interval ab, such that the output there is strictly positive. So f of p is strictly bigger than 0. Since f of x is continuous between ab, according to the theorem, the initial setup of the theorem, it is also continuous between these two numbers n and p. Of course, we don't know which one is the biggest one here, but it doesn't matter. You can just talk about them in general. So it is continuous between n and p. Well, because 0 is between f of n, which is negative, and f of p, which is positive, then by the intermediate value theorem, so if somewhere it's negative and somewhere it's positive, we just use that idea to locate roots here. We know there exists a number, I'll call it r for roots, between n and p such that the output of the function is going to be 0. So if you have a continuous function and it's below the x-axis and then later on it's above, then somewhere in between you need to cross the x-axis, or vice versa. If it starts above and then it goes below, it needs to cross the x-axis. If the function is continuous, it cannot jump over the x-axis because it would break this continuity. So you can only draw the graph without lifting your pen. So if there is a root, then of course this contradicts the fact that my original setup. So we said that suppose a function has no roots. Well, if there's an output where it's positive and there's an output where if there's an input where the output is positive and there's an input where the output is negative, then there's an input somewhere that creates a 0, but that's a contradiction. So this is not consistent with the fact that we're not supposed to get any roots between a and b. So this means that, what was wrong here with this analysis is assuming that there was a negative output and a positive output. It can only be strictly negative or only be strictly positive. Okay, so very powerful statement. And this is all thanks to the fact that the function is continuous. And so sign tables can only be summoned as a tool to study a function if and only if the function is continuous. Anyways, a lot of blah blah here. You don't have to worry too much, okay? But if you're really interested of what's going on here and how these sign tables are linked with the theory, this is the ultimate link. Anyways, so for that section, and actually for that chapter, for me, my job is done. There's more examples you can go through on your own that I will leave you as exercises. 3 very nice examples to work on at the end for the next section to check where a function is continuous or not. But anyways, for me, that's it. That's all. Chapter 3, very short and sweet, but still very important. A lot of nice information, as usual. All of them are very nice. Okay, so all right, that's it. That's all. Bye-bye.